In this problem, we are moving a little bit further along with our projectiles. We're now looking at two-dimensional projectiles. We've already discussed what happens to the velocity and the acceleration in a two-dimensional projectile situation. And so in this case, we're going to learn how to use the average velocity table and analytic solutions to solve questions about a two-dimensional problem. So standard questions that we might be asked is when a ball is kicked at, say, for example, 30 degrees with a speed of 18 meters per second, how long will it be in the air? How long will it take to hit the ground? How far will it land from where it was kicked? And what are its horizontal, vertical velocities upon impact? And what will the impact velocity be? Even the impact velocity angle. So in this case, we're going to start out with a picture to make sure we're understanding the velocity properly. So we've got the ground like so, and we have a ball that is kicked at an angle of 30 degrees. And we know that that initial velocity is 18 meters per second. Now that velocity has two components. The components of it are the horizontal, the Vx, and we've got the vertical, which is the Vz. And those two components are necessarily perpendicular to each other. So of course we see a right triangle. And that right triangle, we can label the sides. So clearly we have our hypotenuse, the side opposite, and the side adjacent. Now we know the hypotenuse, so we're going to use trig functions that have the hypotenuse in them. So those are sine and cosine. So we'll just start out with sine. Sine of theta is opposite over hypotenuse. Theta is 30 degrees, and the opposite side is Vz, and the hypotenuse is 18. So Vz equals 18 sine 30. Now the beautiful thing about 30 degrees, of course, is that the sine of 30 is 0.5. So 18 times 0.5 gives us 9 meters per second. So we now know Vz is 9 meters per second. And if we then move on to the cosine theta is adjacent over hypotenuse. And then the cosine of 30 is Vx over 18. So Vx is 18 cosine 30. And that is not such a nice number. We end up with 15.58845. So these are the components. So like when we had a horizontal projectile that was launched horizontally off a cliff, this is behaving very much like a horizontal projectile off a cliff. It's got an initial velocity of 15.58845. And what we remember is that at any moment in time, that projectile, the only force acting on it is gravity. And so there's only one acceleration experiences vertically. And therefore, the velocity in the horizontal is constant. So we can then put in our velocity in the x direction, which we would say is 15.58. And we might notice then that since we know it doesn't accelerate, it doesn't change, it's going to remain 15.58. And we can then take a look at our velocity in the vertical direction, Vz. Now we know it starts at 9 meters per second. That is the vertical component, 9 meters per second. And what we know about the vertical velocity is it changes by 10 every second. So it's -1 after 1 second. It's -1 after 1 second. So what that means is, if it has a negative velocity, it's already on its way down. So it reached its high point in less than 1 second. And after 2 seconds, it would then be traveling at -11 meters per second. We can then take a look at the average velocity in the z, which is meaningless at 0 after 0 seconds. And then we would have an average velocity of 4 in the vertical direction. 9 plus a negative 1 is 8. Divided by 2 is 4. And 9 and negative 11 is minus 2. Divided by 2 is minus 1. So the average velocity is negative. Now we can figure out the delta x, which is always the average velocity, which in the case of x is constant. So we have 15.58 and we have 31.18 and we have 46.77. And we're being way more precise than we need to be. And then we can find out the delta z, which is going to be the average velocity times the time. So no change vertically. And we have a delta z of 4 meters. And then after 2 seconds, we have a delta z of minus 2. That means it's 2 meters lower than what it started. Well, it started at ground level. So we can see already this thing has hit the ground before 2 seconds. Now, when we examine this, we might say that it's probably closer to 2 seconds than 1 second. So we might estimate that 0 there occurs at maybe 1.8 seconds. The horizontal component will be 15.58. The vertical component, wait a minute, there's symmetry around these things. So the vertical component should be minus 9. Should be exactly the same magnitude but opposite direction of the initial. And our delta x will be somewhere between 31 and 47, so maybe it's going to be something like maybe 42 meters. So how long will it take to hit the ground? About 1.8 seconds. How far will it land? Oh, maybe about 42 meters. Horizontal and vertical velocity, so it'd be about 15.6 meters per second, and it should be exactly negative 9 meters per second. And what will the impact velocity be? Well, let's draw some pictures here. We started out with at V0, we had 18 meters per second and 15.6 meters per second and 9 meters per second. Well, at the end, impact, we have minus 9 meters per second, and the horizontal velocity didn't change, so 15.6 meters per second. So we have the same legs, then the velocity will be the same, 18 meters per second. And whereas this was 30 degrees, this angle here should be 30 degrees. And this angle being 60 degrees. That angle 30 degrees. Oh, wow. So because of that symmetry, we would get the same velocity. And it's important for us to remember up here that we have symmetry. Like so. So this time equals this time. This V0 equals this V. And the same thing with the components. V0 are equal, Vx are equal, and Vz are equal because they're the same height. And similarly, an equal distance in either direction, we would have the same magnitudes in either direction because of that symmetry. Now, if we were to go about solving this analytically, let's see, we've got with 2 dimensions now, we have 2 pairs of equations. So we have our x direction and our z direction. In our x direction, we have Vx equals at plus V0, and x equals 1/2 at squared plus V0t plus xo. In the case of x, the acceleration is 0, and the V0 is 15.58. So our model or equation says that Vx is 15.58, and it doesn't depend on time. There's no term for time. X, 1/2. Acceleration is 0. V0 is 15.58 t, and the x0 is 0. So the position horizontally is 15.58 t. So those are my equations there. Now z, we've got Vz equals at plus v0. And in the vertical, acceleration is minus 10, and v0 was plus 9. So this is our model for the velocity. And our vertical position, 1/2 at squared plus v0t plus z0. Acceleration is minus 10. The v0 in the vertical is 9, and z0 is 0. So we have a model that is minus 5t squared plus 9t. And that's the z of the ball. Now, if we want to know how long it's going to hit the ground, then we know the z of the ground is 0. So using our Desmos, we can put those functions into the equation or into the graphing calculator. And we've got minus 5t squared plus 9t. And when it gets back to 0, it's plus 9. Plus 9, we get exactly 1.8 seconds. T equals 1.8 seconds. And if we just quickly go back to our table, does that agree? Oh, it's exactly what we estimated, given those numbers. That's great. Well, we could take that 1.8 and put it in here. Vz equals minus 10 times 1.8 plus 9. So Vz equals minus 18 plus 9. Vz equals minus 9 when it hits the ground, which is exactly what we predicted from our conceptual understanding. And now when we put that in over at x, we have 15.58 times 1.8. Which is 28.04. And if we I see in my table I put wrong numbers in here. I shifted these downward. These are supposed to be times 0, it's 0, and then it's 15.58. Then it's 31.18. So we might have predicted then that the value is somewhere between 15 and 30, so maybe we'll say it's 29. And what we got in our analytic solution is 28. And the nice thing about doing both a table and the analytic is you can catch mistakes like that one. Whoops, I filled out my table incorrectly. Whoops, I did my calculation incorrectly. And each one checks the other. So going back up to our table now, getting precisely, we know exactly that's the case. Not 42, but it's 28 meters. And the horizontal impact velocities we had correct. And the ultimate impact velocity should be 15 because the components are the same. So we don't actually have to do a calculation for that because the concepts tell us exactly what should happen with that impact velocity. So that is how we would solve a two-dimensional projectile problem shot from ground level and returning to ground level.